Okay, we are live. Welcome, everybody. My name is Alejandro Cárdenas Avendaño, and I'm going to be today's host of this very nice topic and talk by Francisco Salesa. Francisco got his PhD in 2010 from Institut de Física Corpuscular in Spain. Then he moved to Colorado State University as a postdoc, where he worked in mainly two projects, the PRE Auger Cosmic Ray, and also with the HAWC Gamma Ray Observatory, which is what he's going to talk about today mainly. Then in 2013, he moved to Penn State as a research associate and keep working in both in these two collaborations. Then in 2015, he moved to Krakow, Poland as a postdoc to work full-time in HAWC. And then in 2017, he got a joint position, which is similar to an associate professor in this institution, which is the Institute of Nuclear Physics of Polish Academy of Science. Today, he's going to talk about TeV gamma ray astronomy with the HAWC Observatory. The HAWC is the Water Cherenkov Observatory. And so let us just remind you that you can ask your questions using the YouTube channel, or you can use Twitter, and then we will read the questions for you. So thank you, Francisco, Paco, for being with us, and I think it's your turn.
Okay. Okay, so I hope that you are able to see my slides. Okay. There we go. So first, thanks for the invitation. I will be talking today about the TeV gamma ray astronomy with the HAWC Observatory. So I will start with the outline of what I plan to talk about. First, I will give a brief introduction, like what is the motivation and what gamma ray astronomy, we perform gamma ray astronomy. Then I'll talk a little bit about the HAWC Observatory, where it's located, how it's being done, what is the status. And then I will start with some of highlights of the recent results that the collaboration have been publishing and working recently. And at the end, I will mention what are the future prospects of the collaboration. So first, let me start with the high energy astronomy. So here I'm showing the plot of the cosmic ray spectrum. So we know that nature is able to accelerate a cosmic ray to very high energies. By very high, we mean that even greater than 10 to the 20 electron volts. But still, there are things that we want to know that we don't know yet. And for instance, what is the origin of the high energy cosmic rays? What are the sources and how these sources are able to accelerate to such high energy, how they propagate, and even sometimes you can even learn something about new physics from the observation of the highest energy cosmic messengers. In this case, the approach that we have to study to do high energy astronomy is with using different cosmic messengers. For instance, we can directly just measure cosmic rays. The problem with cosmic rays is they are charged particles, mostly protons, that they are deflected by the magnetic field, in the galaxy, for instance, and they are not pointed back to the source unless you are at very, very high energies. So this is, for instance, what is trying to do the PRE Observatory or the telescope array. Or then you can use other messengers, for instance, gamma rays, that this will be what I will be talking today, especially with what we do with HAWC. And also, as you probably know, there is also a neutrino detector like IceCube and TARES Future Cam3Net. Are also more recently, they joined the party by gravitational waves. my LIGO and Virgo detectors. Sorry. So yeah, and this slide is like a little bit like we are going to be focusing photons, especially at the high energy. So this basically reflects how light is absorbed in our atmosphere. So unlike visible light that you can just use your telescope at home and you can just point to your sources, and gamma rays, they don't make it up to the ground, fortunately for our health, in fact. So if you want to directly, detect the primary of the gamma ray, you need to use the natural way to detect them will be just send satellites. Okay, so in order to, because the gamma rays interact with the atmosphere and produce a shower of electromagnetic shower. So you want to have it, you want to detect the primary, you basically need something up in the atmosphere. So in slide 5, I will be mentioning what is the ways, the current gamma ray observatories, how they do this thing. So the first method is like the natural approach, I would say. You send satellites, and they are very nice. They can detect the primary gamma ray. They have a very good energy and angular resolution. But the problem is that you cannot send very big detectors to space. They are expensive to send up there, and you basically end up with detectors that are of the order of square meters. So if you want to go to TeV sensitivity, basically your detector is too small and you run out of statistics. You cannot detect because you are run out of statistics. Then the approach that we do is, okay, we construct, instead of detecting the primary, we detect the secondary. Basically, we have the gamma ray that interacts in the atmosphere, typically like at 10 kilometers high in the atmosphere, from the sea level, and then there is an electromagnetic shower that develops. So for this electromagnetic shower particles is the ones that we want to detect in these ground-based arrays. And this ground array has, the limitation is just, they are, you can just build them big, and you have in order to go to TeV sensitivities. In this case, there are two approaches. One that is called Cherenkov telescope. So basically, you have your primary, you have your electromagnetic shower that develops in the atmosphere, and then there is Cherenkov light, because these particles are very energetic. And this Cherenkov light is catch by this Cherenkov telescope. And a typical example of that are HAWC Magic or Veritas, and will be the technique that will be used in the future Cherenkov telescope array. These detectors are very nice, and they have a good energy and angular resolution, but the drawback is that they have a reduced field of view, so they basically need to point to the source. And in addition, they can only operate when the atmospheric conditions are good, and for instance, you cannot operate when there is daylight. Sorry. Then the other approach is what I will be talking today, is HAWC Observatory, that is called extensive air showers. In this case, we detect the Cherenkov light, but we detect the shower, but at the ground. So we have our detection units that will be water Cherenkov detectors. So we detect the Cherenkov light that is produced inside the tanks, these water Cherenkov tanks. In this case, the advantages of that is we have a large field of view, and we can operate almost 24/7. We have a high duty cycle. And the drawback then is that our angular and energy resolution is not as good as, for instance, the Cherenkov telescopes. But at the end, as we will show later, basically we can complement, the different detection techniques can complement each other. So here I will just present some of the HAWC scientific goals. So because of this large, it's able to have the large field of view, and it's able to operate almost 24/7. One of the scientific goals when we talk about galactic sources is that we can do a plane survey of the galactic plane, and we can be we have very good sensitivity at high energies, and the order of more than 10 TeV. Also, since we have a large field of view, we are sensitive to sources that are, for instance, difficult to detect, or for Cherenkov telescopes. And in this case, this example is the Geminga region, or even the Fermi Bubbles. Okay, and then if we talk about extragalactic sources, then since we have a high duty cycle, we are operating most of the time. We are also advantages because we can monitor the AGNs. We can produce a light curves of the AGNs. We don't need to take data now, stop the detector, because now we cannot take data and then take the following day. We basically can take all the time he asked, I mean, if the source is up in the sky, we can just take data, regardless of the conditions. And also, it's very good if we want to try to catch gamma ray bars. You know that gamma ray bars occur in positions that are not predicted in the sky. So, I mean, if you have a large field of view, your chances of catching one of them are basically better. And then it's not only in gamma ray astronomy that we can do. We have a huge background of cosmic ray that I will talk a little bit later. So we can still do some cosmic ray physics, and also even some fundamental physics, like trying to search for dark matter, like from annihilation or decay of dark matter, trying to cut a gamma ray signatures. One of the things that we are also very interested in is in working in multi-messenger, or we have a lot of memorandum of understanding with other experiments. For instance, with Cherenkov's telescope, we share our results privately. So we have like, okay, these are the sources that we see. These are interesting sources that we might want to look and study. And also we have that like with particle detectors like ice cube or even gravitational waves. And I will give some examples later in the talk. So then talking about HAWC, the HAWC collaboration is mainly US and Mexico institutions. And more recently in 2016, it was joined by the Institute of Nuclear Physics, that is the one that my home institution now, and also by the Max Planck Institute in Heidelberg in Germany. And this here you can see like a picture of one of the recent collaboration meetings. So the HAWC Observatory is located in central Mexico. You can see there like a zoom in the region is like in the state of Puebla. Is next to Pico de Orizaba. Pico de Orizaba is one of the highest peaks in North America. And it's like in between the Sierra Negra volcano and Pico de Orizaba. It's like in a slope of the Sierra Negra volcano. And it's also a place that, in fact, at the top of Sierra Negra, you have the Large Millimeter Telescope that is another telescope, but this is for lower energies. So here you can see a zoom in with a picture of the detector. We have all these water Cherenkov tanks. And I put like a scheme here. You can see to guess, I mean, the size is 5 meters every tank, and it's full of water, and they have 4 photon multipliers inside that are distributed like in a triangle with one at the center. So just a little bit, I mean, how the detector looks like. So this is how a water Cherenkov detector is. This is you have the steel frame, and then you have like a big plastic bag that goes inside and is full of water. And we have water that we're going up to the mountain with trucks. It's a huge amount of water. And this 200,000 liters per water. So we have 300 of those at the site. And then the instrumentation is 4 photomultipliers. 3 of them are 8-inch photomultipliers that were reused from a previous experiment, from a Milagro experiment. It was basically the predecessor of HAWC. And one this brand new 10-inch photomultiplier. Okay, so then about how we detect gamma rays. So we have the cartoon on the left. So basically you have your primary that arrives, interacting the atmosphere and produce this electromagnetic shower that develops in the atmosphere. So we want to catch this at the ground with our array of detectors or detector units. So basically at the end, you know the position of your detectors, your photomultipliers, you know the timing when you have the heat, you know the charge. So you basically are able to reconstruct the primary. Okay, so what is the energy and what is the direction of the primary gamma ray. And one of the things that's important to mention is this detector, you want to build it as high as possible. So in the plot that I'm showing here in the middle and the bottom in the middle is how the number of electromagnetic particles, so basically how big is the shower, depending on the distance from the interactive point. So basically, if you have a detector at the sea level, you see 2 orders of magnitude less particles that you catch if you are at the altitude that the HAWC is. And as you can imagine, this is good because the more particles you have, the more information you have, and the better you can reconstruct your primary. And here, one of the things that is one of the main challenges of the detector is is to discriminate between gammas and hadrons. Because the thing here is that we have a huge amount of gamma rays, of hadrons. So we have like 15,000 cosmic rays per second that are reaching our detector, and from one of the brightest source in gamma rays, that is the Crab Nebula, we expect only 400 gammas per day. So as you see, this is like several orders of magnitude, this background. So the way that we want to discriminate that is, okay, you can see that they are, in fact, the showers that are developed from gammas or hadrons are slightly different. And thanks to this, we are able to discriminate gammas from hadrons. So on the left, you have what is the result from a simulation, but on the right, you have real data. And this is our event display. So basically, the size of the circle that you can see there, these color circles, represents the charge. I mean, it's like a factor of the charge. It's kind of proportional to the charge, right? So the bigger means like a big charge. And the color means the timing. So in the gamma case, you have most of the high charge hits are in the center. It's like more compact. This is what you expect from electromagnetic shower. But in the case of hadrons, you expect that this shower is like more like break apart. You have like muon contribution outside, let's say. So it can lead to a high energy, high charge hits outside of the quite distant from what is the reconstructed core here. The reconstructed core is this red star. So based on that, based on the pattern of the the footprint of the shower that lives in your array, you are able to discriminate from gammas to hadrons. So then, now that you more or less know how HAWC works, I will go through some highlight of some of the results that we recently published. So on the left here, you have, you can go to the list of all the publications that we have. Most of our publications were done the previous year, and they are happening now. So now it's like the time where we are more active, in fact, because I think I forgot to mention, but basically HAWC was completely operational since 2015. So we have like 2-3 years of data accumulated. So now we are when they are delivering the results. And one of the nice features also here is that in our web page you have also the access to some of the data that were used to produce some of the papers that we presented. And for instance, you can see here like what is like a sky view. So you have even the catalog that we publish with the sources that we see. You can just go there and you select your position in the sky and see exactly what we saw in our data set. It's quite nice. Okay, so first thing is that HAWC SkyMap. This is the most recent SkyMap. These are galactic coordinates. Okay, the big holes that you see there, the white holes, is basically these things that are out of our field of view. Okay, because we are basically the Earth. You are part of the sky that you cannot see. This is what these white holes represents, right? And this map is done in significance. So the sources are basically this yellowish white thing. So here you can already recognize probably some of the known sources in gamma rays. For instance, the Markarian blazars. These are known active blazars at extragalactic. Also, you can recognize the galactic plane. So this is galactic coordinate, right? So you have at 0, you have basically the galactic plane. So you have most of the sources are detected in the galactic plane. And then there is also the Geminga Region or the Crab Nebula source. And yeah, in this slide, what I'm showing just a comparison what the gamma ray SkyMap looks like for Fermi. This is 5 years above 1 GeV for Fermi compared to HAWC and also with HAWC. And HAWC is like a pointing instrument, so you don't have like the whole sky, and you have like basically the places where you have looked at. In this particular case, I'm showing just the galactic plane because they did a deep survey along the galactic plane. Okay, but you can more or less see the difference, and this implies also different energies, and this is what I will mention here also in the HAWC sensitivities. So this plot reflects what is the flux that you need from a source in order to you will detect at 5 sigma. Okay. And this, you can see what is the sensitivity of Fermi, that is at lower energies. Then you have the Cherenkov telescopes like HAWC, Veritas, and MAGIC, the ones that are operating. And then you have HAWC. So one of the things that I mentioned here is that the Cherenkov telescopes are more sensitive, have better energy and angular resolution. So they are instantaneous sensitivity is better than for instance, the extensive air showers like HAWC. Okay, but we have in advantage, we have a large exposure. We can operate all the time. So, I mean, you cannot compare one day of data of HAWC with that data of Cherenkov telescope. That's the point. So you usually compare like 5 hours of observation, which is quite a deep observation for a Cherenkov telescope, with, for instance, 1 year. And in this case, I'm plotting 507 days because was the first catalog of HAWC was done with this number of days. So it's 1.5 years, more or less. But you can see that also the take-home message here is that about 10 TeV, basically HAWC sensitivity is comparable to a deep observation from a Cherenkov telescope. So basically, about 10 TeV is one HAWC. I mean, it can have like an important contribution, let's say. And this slide is what I'm showing here is the Crab Nebula. So the Crab Nebula is a very well-known source in gamma rays. Okay, so basically we use that source, observing that source to test our angular resolution, for instance, to test our Gamma-Hadron Separation and also improvements in our energy resolution. So what I'm showing here, this is called bin 3 and 8. So the way we analyze our data, we basically bin our events depending on the size of the events. So the smaller the size, the lower is the bin, which is basically when the smaller the size of the event in the detector means that the energy is also smaller, right? And the higher the event is, and they have more PM test hits in your detector, it means that the primary has higher energy. So you can see there, this is not a significance, but event map. So you can see like a clustering of events from the position that the Crab Nebula should be at the center of this map. And you can see the clustering of the events, and you can see that they cluster differently for bin 3 and 8. So basically, from that image, we can more or less get what is our angular resolution. And if you define your angular resolution with the criteria of 68% containment of the events, basically you have like of the order of 0.25 degrees for events that are hitting the detector like 50% of the half size of the detector. When you have events that hit 50% of the detector, your expected angular resolution is 0.25, and you have even higher energy, your angular resolution can even be slightly even better. That's one thing. Also, one thing that is nice is that at high energies, our signal to background discrimination reaches the order of 10 to 1, which, as I mentioned before, if you remember, I was mentioning that we get several order of magnitude more cosmic ray than gamma rays. And our selection cuts, at high energy, we are able to reach a signal to background ratio, which is 10 to 1, which is really nice. And finally, the plot here is our measurement of the Crab spectrum, the Crab Nebula spectrum. So the solid red line is the fit, the red band is the systematic error, and the light red band is, there's the statistical error, and the light red band is our systematic. And this is compared with measurements from other experiments. So basically, we have good agreement. Then one of our results was also we observed the sky, and we released the catalog of the sources that we observed. So this is the zoom in the galactic plane region where you expect most of your sources to be. And here we basically have tags of the sources. The tags on the upper part are sources that were already known before HAWC. And the sources in below are the sources that were detected by HAWC. And so this is for half of the galactic plane, is for part of the galactic plane, and the one in the bottom is for another part of the galactic plane. So the next thing here is that we were, in our catalog, we were claiming 39 sources, but out of these 39 sources, there were 19 that were without a counterpart of TeV energies. And by counterpart, we define that there are sources that are detected at least half a degree away. So basically, we are seeing regions of emission of gamma rays that are of interest to study. Okay, this is a more recent map, so I just go back and forth. You can see that the increase of the significance. So basically, it's with twice the data. This is the most recent map. And for instance, things that you can study from our observations is like trying to see what are these new sources. So for instance, we have this HAWC 1953 source that was not previously known, but was not detected at TeV. And we share information with other instruments, as I said at the beginning, so with Veritas, HAWC, MAGIC, and Fermi. So they can look at our source. And this is very nice because it was like the first source that we detected that was not detected, and they were able, you can see this yellowish region. This is a significance region that was detected afterwards, after the MOU with Veritas, that were able to also detect this source. That they observed this region, in fact, but they didn't observe enough time. So since we point to that interesting region, they would take more data, and they finally saw that this source was showing up. And not only this, but there are also other different regions. I just highlighted another one, which is quite interesting also. And that is first, there is one source that is detected already by other TeV instruments. But there is another source that's kind of next to the other one that is in fact more significant for us, that is not seen. So, as I said, HAWC discovery triggers other instruments' observations, and for instance, Cherenkov telescope can perform a more detailed observation. So so the sources that were, interesting sources that were discovered by HAWC were being observed by other instruments, and we have a couple of papers that are in preparation and hopefully will be submitted soon and published during this year, where we have observations from Cherenkov telescopes and for Fermi observation of the HAWC sources. Okay, moving a little bit forward, we have the Geminga region that we observed. This is a very interesting region also. First thing, this Geminga was detected by Milagro, the one that was HAWC predecessor. This is our maps from Milagro here. This is what you see if you have to perform a point source analysis. The funny thing here is that the emission is very extended. So being very extended was challenging for Cherenkov telescope, so they were not able to detect this emission. And only after HAWC confirmed, only HAWC came later of Milagro to confirm that source. And this is what observed by Milagro after 8 years of observation. With Milagro was like an order of magnitude, even a little bit less sensitive than HAWC. Okay, so this extension is interesting because it's like 2 radius extension, but with what you see in X-rays is an extension that is of the order of arc minutes. So basically, something like it's 2 orders of magnitude larger in gammas than what you see in X-rays. So because of that, was suggesting that these regions can be what we was probably going on there is that you have the electrons that are accelerated by the Geminga pulsar, and then probably this is what you see is that like gammas producing after inverse contact of these high energy electrons. And it was very interesting because you have like a nearby source that is producing leptons, and this can be like, I was pointed by some theoreticians, like can be like the reason why you see the Pamela positron excess in the cosmic rays, right? So we have this positron fraction that you expect to decrease, but suddenly about 10 GeV, you see an increase by Pamela that was confirmed by MAS and other experiments that was not expected. So Geminga was confirmed by HAWC. This is a map from HAWC It's a significance map. It's under a point source assumption. The white contours are the after extended morphology assumption. So these are 5, 7, and 10 sigma contours. Okay, but not only that. Apart from Geminga, there was also we also found a similar extension for the first time from the pulsar HAWC 56. Also, people know about like monogen. So this is very interesting because both pulsars have been like one of the main candidates. If if this astrophysical source producing this positron fraction, many authors were pointed to this to be the main suspects. Okay. What we measured with HAWC, we were able to measure that, and apart from measuring the flux, we were able to measure the profile distribution, and we just discovered that it's very extended. It's about 5 degrees, and if you think about 5 degrees, how extended is that? If we were able to see the gamma ray sky, you will see that the Geminga region is about 10 times the moon size. Okay, so it's very, very large source. And then you can understand why it's difficult for the Cherenkov telescope to discover. So from this radial profile, okay, because you have the gamma emission is associated with the electron and positron accelerate, right? So from this gamma profile, you can infer what will be the diffusion coefficient. So your model is basically that the particles are diffusing away, accelerated, and are diffusing away from the pulsar, and you have gamma rays thanks to the inverse contour. You have gamma rays accelerated, for instance, picking up background CMB photons, ambient CMB photons, and then you can accelerate that to gamma rays energy. The thing here is that the measured diffusion, I mean, we found out that from this profile that the diffusion is like slower than that was thought. So from the information that we get from the flux that we measure on the profile, and under our assumption that was like there is isotropic and homogeneous diffusion from these sources, then we can estimate what will be the positron flux at the Earth, and is this plot here. So this blue solid line is what we expect from our observation, and we tested different things, like for instance, what will be the different assumption from the luminosity of the pulsar, and different assumption of how the diffusion coefficient changes with the energy, and also the systematic errors, that is this black line, and also the statistical. But at the end, I mean, our observations were unable to explain what we see the positron excess. And it was published in Science by the end of the last year. So then the question is, well, where is the positron excess coming from then? So first thing that we want to mention is that we only studied 2 sources. It's true that it's 2 pulsars. It's true that they are the main suspects, but there are other sources that can be contributing. In fact, there is a paper that was published by Linden et al. after our catalog, that we were predicting that we will see similar TeV halos from other pulsars. And in fact, they even predict that even pulsars that are not beamed to Earth, that are difficult to detect by other counterpart wavelengths, that they call invisible pulsars, can be, thanks to this extended gamma ray emission, can be detected by HAWC. And in this plot, what I'm showing here is what they did, and this is from this paper from them, is basically they put like 80 NF pulsars. So basically 80 NF is a catalog of pulsars. It's the gray dots. They highlighted in green the ones that are in the HAWC field of view, and they estimated which ones probably we should be able to see if this is, these are emitting these TeV halos. And in fact, one of the sources that we didn't claim in the catalog, and we discovered later, and we guys basically released in an astronomical telegram announcing that, is one of these sources that we're mentioning here, which is a source that is kind of next to the crab and is also measured like extended. So yeah, we are likely to catch and discover more of these TeV halos from pulsars. Also, one of the, it's always one of the hypotheses can be like this positron fraction can be from the annihilation or decay of dark matter into standard model particles, or even there are recent papers also, some after our publication, that they claim that, one way to explain that is you have like our assumption that the diffusion constant is, is constant. That does not change. Is not true, but you have like a different diffusion constant next to close to the pulsar somehow, and then you have a different diffusion constant. So there have some papers that have been written that they think that it still can be explained with Geminga, but you have to take into account that the diffusion constant is in fact it can change. And also there are other theories that this like can be other cosmic accelerator, not only pulsars, and also even theories about secondary production. So I'll not extend more on that. I will now show you also, because we have large field of view and high duty cycle. We want to measure transients and do multi-messenger analysis. Fortunately, we don't have any detection yet, but we were trying to look at some interesting ice cube neutrinos. For instance, the plot on the upper right is one multi-PeV neutrinos detected by ice cube. So this is a very high energy neutrino, and the good thing is a muon neutrino, and this probably the muon neutrinos have a better localization, a better angular resolution. So it's easy, you don't have to look in a large extension, you have less trial factors. And so we looked there, unfortunately we didn't see anything, and there are other interesting events like multiplet of neutrinos that were kind of close in time, and also in one recent ice cube neutrino that has a likely gamma ray counterpart. Unfortunately, we look at all them. We have a.s.l that we sent, even a paper here, also where we didn't see anything. Also, we are trying to catch gamma ray bursts. We have a recent paper also published last year where we study the gamma ray bursts from triggered by other experiments, like, for instance, Fermi, and we observed some of these gamma ray bursts, but we didn't see any indication yet of TeV gamma ray burst. And then it's very nice also gravitational wave. We have events that were, detected by LIGO and Virgo, and we studied some of them. Here I show one of the one that we studied. That was the trigger time was fall within our field of view. So this blue line is the HAWC field of view. These red contours are the most probable location of the gravitational wave happening. Our best candidate was like a spot that have a 0.08 p-value post-trial significance, but it's not enough to claim anything. And we also observed this very nice event, that is binary neutron star merger, but unfortunately it was out of our field of view at the time of the trigger, and we were only able to measure that now hours later. So we were only able to set upper limits. And also this plot here is kind of nice plot where we this is the sensitivity depending on the zenith angle at different assumptions. What will be our capabilities to detect a short gamma ray burst. Short gamma ray burst is probably what you expect from a gravitational wave event. And for a nearby gamma ray burst, and it's like redshift up to 0.1. Okay, so see that we plot a couple of gamma ray bursts that were detected by Fermi-Lab. So we should be sensitive to such type of short gamma ray bursts if they are high enough and they fall like in a good zenith angle for us. So basically, we are just waiting for the more events from LIGO and Virgo. I think it will happen in fall. They will start taking data again. So we are just waiting for more events and increase our statistics. So I will try to go because I think I'm running already a little bit short on time. So just mentioning that Markarian Galaxies, they are AGNs. very well known and extragalactic, but the advantage of HAWC is that now we can monitor it unbiased and continuously. This is a light curve that covers more than 1 year and a half, more or less. And you can see that you have this, you can see like high variability. In fact, this curve that is inconsistent with constant flux by more than 6 sigma. And you can see like different like flaring events. So now we are even able to detect these flaring events and send alerts to other experiments to tell them that this is something interesting happening. You should observe to that source. Also, like just quickly, Fermi Bubbles, as I said, we have a large field of view, so we can cover part of the North Fermi Bubbles. If you're just probably familiar with Fermi Bubbles, are a large and symmetrical structure that extend 5 kiloyears above the galactic plane, but were detected by Fermi. So, I mean, this is a good candidate to be detected by HAWC. In this plot here is what we are able to get. We didn't see, we have no detection, but we were able to infer relevant upper limits. So these dashed lines, the dashed black lines is like the upper limits that we get with HAWC, and we have the points by Fermi and different models that are trying to explain the data. And with HAWC, we are already able to constrain a couple of models. There are some models that we are not able to constrain yet, but at least some models we are already able to constrain on this, more information in this publication. Then also, even if it's not a dark matter detector, with HAWC, you have like a large field of view. So there is in this map, you have good candidates that are expected to contain a large amount of dark matter and having like low luminosity in gamma. So you are very good target to study. So we study some of them, have some publication. I will not spend much time here, but basically we were able to set upper limits in the cross-section and the lifetime, so annihilation and decay. And these limits basically complement other experiments that are quite competitive and relevant for what the dark matter masses are more than 10 TeV. Also, even if it's not a cosmic ray experiment, as I mentioned before, we have a lot of cosmic rays in our data. So we can use them and we can perform still physics with cosmic rays. So for instance, one of the nice things that was discovered in Milagro and was then verified by HAWC is that there is a cosmic ray anisotropy. So this map here, this is the intensity. So there looks like we get more cosmic rays for some direction than the others. But this anisotropy is seen at large and the small scales. This is a plot of large scale. Okay, so we see that the blue line is like a kind of deficit, that you expect from isotropy, and this reddish is what like excess. And we published a paper already. One of the analyses that's very nice. We are combining data with ice cubes, so in order we can cover both hemispheres, the north and the south. And this is a preliminary plot also what is HAWC and ice cube combined analysis, and it will be also a paper submitted very soon, and we will have a paper probably this year. And also we can detect the moon shadow, which can be the cosmic ray moon shadow. It can be used, is the plot here, can be used for validate our pointing and energy response. And also we can even put points on the all particle. You remember the plot that I showed the cosmic ray at the very beginning. So there is a range of energies that we cover, and we can measure the all particle cosmic ray spectrum. And this was also a publication that is this blue dots, and this is the systematic error that in our measurement. And now briefly I will comment a bit on the papers that will be publishing, submitting and publishing probably this year. One is the signal region. This is a very interesting region, is the region on the left. Fermilab discovered a cocoon that is a region that of star forming region that is good candidate for for cosmic ray acceleration. The nice thing is that it's large extended, so we can be detected by HAWC, and it will be nice and interesting to see what is the maximum energy, what is the spectrum that we can measure with HAWC, if there is a cutoff in the energy, and what is the implication this cutoff can have. And also there is another source, that's Milagro 2019, which is extended a very hard spectrum. And also this, and next to them, there is another source that is quite nice also because it's extended but has no counterpart. And is one of these, I mentioned, invisible pulses at the previous in the talk, and can be also like a good, nice candidate for that. Then another nice source is SS433, which is an X-ray binary. And we have an indication of a first TeV emission from the lobes. There was a 4-sigma trial hint by Veritas that was announced in the ICRC, but we now have like a detection, a TeV, and about preliminary results. It seems that leptons models of emission of gamma rays may be favored for that source. But as I said, this is work that will be finished soon and will be submitted to the journal. So you will have to wait for the final results during this year. Also, a very nice thing is the high energy. So I will not extend much here, but basically we are improving our energy reconstruction, and we will be sensitive. We are sensitive to very high energy, so about 50 TeVs. So basically, at this energy, basically HAWC is the one that outperforms any other gamma ray detector right now. We can even see a very huge event from the Crab Nebula. We can detect the Crab Nebula more than 10 sigma, and we have very interesting sources that we can see. Some of that are known. It will be interesting to see how I are detected and what is the spectrum and how what is the maximum energy and how long this spectrum extends to higher energies. Because these are very good candidates to be pevatrons, like the cosmic ray acceleration in the galaxy. So it will be nice to study them. And just very briefly, I will comment a little bit about the future of HAWC. So we are already deploying what we call outriggers. So our triggers are small water Cherenkov tanks. You can see from these pictures. So we finished deploying all of them. So this is the main array and the small water Cherenkov tanks. We are now in the instrumentation phase. We have 40% of them already instrumented, and we expect to have them fully operational by the end of this summer. The nice thing of that is that there are some events, especially peak events, that where you have like your detector can see the hits from the shower that is produced by the primary, at the very high energy primary, but your core is reconstructed outside the array. So your determination of the position is not very good, and your energy determination and location of the position of the primary is not very good. So with these outriggers, we will improve our effective area, especially about 10 TeV by a factor of 4. So it will be very nice for studying these high energy sources that I just mentioned. And if you look in the more like long-term future, there are plans in the collaboration together with other external, it's not only HAWC, but other external physicists, experimental physicists, to build what is called a Southern Gamma Ray Survey Observatory, which plans to be like similar to HAWC, but in the south. And now they are discussing on what will be the good, better side. I mean, there are candidates in Argentina, even Chile, that to be like a good site. So you have like high altitude enough to, to host this type of detectors. And will be nice because with that we will have a full coverage together with HAWC, and we can be a very good complement for the south version of CTA. And we plan some improvements on that, not only just with the same thing. We plan to go higher because higher is better, because you can detect more particles for the shower and have a larger area. So yeah. So the summary, I think I will skip because I'm running a bit, I think, short on time. Basically, you can read that later. I will be posting the slides. And yeah, and now I think I would like to thank you for your attention, and I will be taking some questions that you have, trying to solve them. Thank you very much.
Okay. Thank you. Let me see. What's going on? Okay, thank you very much, Paco, for this very interesting talk about all this cool science that has been done already and all the things that are going to happen in the near future regarding particle physics. So yes, the slides will be posted later. You can check that in our channel. So we can start with a few questions from our coordinators. Do we have questions, guys?
I have one. So thanks, Paco, for the super nice talk. So can you please go back to your slide 29, I think, where you show the dark matter limits?
Mm-hmm. Yeah, let me, just a second, I need to share the screen again. Sorry for that. Let me put in full screen. Yep.
Yeah, so I cannot see the axis. The mass goes till 10 to the 5 GeV.
10 to the 5 GeV. Yes. That's correct. This is GeV. So basically, this is a 1 TeV. This is
100
10
TeVs.
TeV, and this is 100 TeV. So our lines are the solid lines, and the different lines represent different targets.
I see. And the lower plot is?
Yeah, I mean, you know, in the publication you have, yeah, it's a bunch of plots. You have different channels. This I pick just one, like a example. This is BB bar, and the one on the upper part is annihilation, and the one on the bottom is decay. But I mean, in the publication you have other channels that were tested for study.
Okay, I see. So these are the actual limits, not projections.
No, these are limits. These are upper limits.
I see. Okay, thanks.
Okay. Do we have any other questions? Let's check. Okay.
Can you hear me?
Yeah. Yes, Camilo.
Hi. Hello, Francisco. Thanks for the nice talk. I have 2 questions or 3 questions. So one very basic one. Concerning like the physics of these detectors, what can you do with a water Cherenkov telescope that you cannot do with a telescope like HAWC or with CTA? So what would be the main difference between what you can do with those things? So that's one of the questions I have. Okay,
you want me to answer that first?
Yeah.
So, okay, so the thing is they have different properties. So a Cherenkov telescope is very good. I mean, they can study better the source. But there are things like monitoring of the light curve, for instance, of the blazar, you cannot do. I mean, you can catch part of the light curve, let's say, but you cannot spend your money building CTA and be pointing all the time to Markarian Galaxy, right? And this can be done, for instance, with HAWC, because you don't need to point, we have the data there. I mean, you just need the source to be up in the sky, and that's it. So one also, I think, is very important. So we have an unbiased light curve monitoring.
So HAWC can collect information from the entire sky, whereas these telescopes just point to a fixed direction.
So they have targets that are interest for them, and they schedule. They have like a schedule of the time. They have limited time, but they have to schedule what do I want to see tonight, because they observe at night. You need the dark sky, so they do, okay, tonight we are going to observe this source. We are going to scan this part of the galactic plane. So they do these things. Or for instance, there is an alert that Markarian is flaring because HAWC saw that flaring and say, okay, go fast and point to that source. Or let's say there is a neutrino that is detected by the ice cube, very interesting. So they go fast and they point to that. They have like kind of priority list, let's say, and then point to that source. This is how this telescope works. And the drawback is that they cannot point to all the places, right? But on the contrary, HAWC can point to all the places, but the drawback is that it's not as sensitive as these telescopes.
Okay, thanks. So that was my first question, and my second question has to do with this these results that you were mentioning concerning Geminga and this other pulsar. So as a hypothesis for explaining the excess in Pamela. So my question is, why do people discuss these two particular pulsars and not other nearby sources?
Okay, so the interest of these pulsars are two mainly. One is that they are nearby. So we are talking about 250 parsecs, which in cosmic scale is our neighborhood.
But so are they the closest to us?
Yeah, they are not the closest, but very close. But it's not only this. I mean, you have to be like powerful, let's say. So they have like spin power, also energetics, matter, and also matters that they are old enough. Because if the pulsar is very young, these particles didn't make it to the Earth yet, right? These pulsars are of the order of 10 to the 5 years. So the electron diffusion, I mean, they have enough time to diffuse away and finally reach the Earth. Okay, this is why, I mean, the main two reasons. One is that they are nearby and they are old enough to be able to produce. I mean, because they need to be like the right age. Because if they're too young, they basically didn't reach, these particles didn't reach the Earth. Okay. And if they are too old, they are vanished and you don't detect them anymore.
So it's not possible to, let's say, try to explain the Pamela excess with other pulsars that are closer to us just because they are not rotating fast enough. Is that the
I mean, for the ones that we see, these ones are the best. My personal opinion is we have the south to explore yet. And in fact, this Geminga pulsar was only discovered by Milagro. I mean, it was unknown until then. I mean, not the pulsar, but, you know, this big extended region in gammas. Until HAWC didn't come, and so this is true. I mean, it's something that is happening. We didn't know about that. And it might happen that also there are sources in the south, and maybe have like contribution of other pulsars that we, as I mentioned before, we didn't discover yet, that they're making a contribution, and they have a lot of them that can be contributed. And this was some of the hypotheses that people say that, yeah, when you have a lot of pulsars and they can at the end contribute. But I mean, one of the main hypotheses was they say that Geminga was the main culprit, let's say, and the other ones were contribution, increasing also the positron flux. I mean, there are theoretical papers that they put the Geminga contribution, the other pulsars, and they make it able to match the Pamela excess.
Okay.
But as I said, I mean, these two are more interesting because of these two properties. They are nearby and they have like the right age, let's say.
Okay, then, and my final question in just 1 minute. So you were saying that in the near future there will be improvements so that HAWC is some sort of a counterpart on the northern hemisphere of CTA, right?
Yep.
So what could you do if that's the case? I mean, if CTA has a counterpart in the northern hemisphere. So in other words, what would happen if there is no counterpart of CTA on the northern hemisphere? What could we miss?
Yeah, I mean, that's the thing. I mean, this is like, well, I mean, the physics case is one of the things that is being studied now, and this is what you want. And this is because, I mean, the detector is not designed yet. So we want to have a detector that is able to provide useful physics apart from CTA. So one of the things is that they can make it higher altitude to make it more sensitive area. Depending on how you distribute the tanks, you know how they packed they are. You are also sensitive to a different range of energies, lower energies of higher energies. So these things are still not decided yet and are being discussed, as well as the site. But for sure, things that will be able to help is like for like transient sources, like the CTA still will be a pointing telescope. So there are transient things that probably are going to be hard to do with CTA, and still HAWC can do. And also it will be explored of the south without any bias, so we don't need 2 points. So there are sources that, I don't know, maybe there is like, we have also like, for instance, self-triggered alerts. Let's say happens something gamma ray bursts, and we are able to detect in the HAWC South because it's more sensitive than the HAWC, let's say, is an order of magnitude more sensitive, but we are sensitive to gamma ray bursts, and we see like, I don't know, 10 in a year. Then, I mean, this is very important to have this detection and see if IceCube can see them also. And for CDA, you will need to point, and it's not going to be trivial to catch one of the gamma ray bursts. So, I mean, as I said, there is still not planned. There is still planning how the detector will be the physics case of the detector. But yeah, in principle, there is still room for things that we can do. And besides, I mean, of CTA.
Okay, thank you very much.
Thank you, Paco. I think we have time for one question that was made on the YouTube channel by Mukarbek Organov. I apologize for the pronunciation. And you can, Paco, you can read the question on the group chat, which says that do the light curves or some sources already available up to 2017? For example, as from Daily Monitor paper for 17-month Markarian 421.
In fact, I got, yeah. So the light curves, you want the information of the light curves, right?
Yeah, and so, it's asking if it's not available even via public.
It is, in fact, and it's a question that they usually get because people are interested in this information. So there is this public data. I just put the slide 12.
Okay, let me present you. Done. Okay, yeah, we can see it.
So basically, you have I mentioned only the catalog, but there is Geminga paper, so you can even reproduce, because it's a requirement by science, in fact, that you provide the data set and the code that you use, so you can reproduce the result. And this also that is called light curves. So there are ASCII files where basically the points that I show there, you have these points, like in I think it's ASCII file format. These points there in this plot, they are there. So you can get this information there. There is even a README file that explains you what is the meaning of it. So you have there the information, so you can access that in our public page. Yes.
Okay, perfect. I think that answers the question for this person. Yeah, perfect. Okay, so thank you very much for this night talk, Paco. This was really nice. So thank you everybody for tuning in today. Our next webinar will be next in 2 weeks by Xavi Bertu from Centro Atómico Bariloche, and then the next one is going to be by Edgardo Sheteha from Maple software, talking about how to do physics with Maple software. So stay tuned. Remember to follow us on YouTube, Twitter, and all our social media, and stay tuned. Thank you very much. Thank you, Paco.
Thank you.